Hi there, and welcome to this midterm solution video. Thank you for tuning in. The first problem is a theoretical linear algebra problem. It's 8 points, and as I said in my email, I feel like you guys are doing worse overall on the linear algebra stuff, but better on the Fourier series stuff. So I think that's probably just a small sample size, because the videos, materials, assignments are all the same, but the stuff is on the final, so I want to make sure you understand it. And it's something you can totally pick up if you don't quite have it. So first of all, this is we're looking at the vector space of 2L periodic functions. So think like sines and cosines and square waves and triangle waves. This is an infinite dimensional vector space. So a basis is going to have infinitely many things. And a basis consists of functions, not of things like 1, 0, 0. That's not a function. That is an element in R3. It has nothing to do with a 2 pi or 2L periodic function. So a basis, and we said this in class, this is one of the emphasis points of Fourier series, is the space of all exponentials, e to the I pi nx over L, where n is some integer. So there's infinitely many of these things. And that right there was half the credit. Find an orthonormal basis. That's like 4 points. Some people, I don't know if you didn't read this or didn't know, but just didn't even answer that part. Like, that's the first sentence. Find the basis. And then how would one verify that the basis is orthonormal? Now some people, I think, got this right and didn't do the second part, or vice versa. I don't think anybody got full credit on this problem. But together as a class, every part was answered by somebody. So how would one verify this basis is indeed orthonormal? And it should not involve the term inner product. Like, one of my 1080 calculus students should be able to understand how to check this, even if they don't know what it means. And I'm not sure anyone's answer was really something that could be understood by a calculus student. And so what I'm looking for here is orthonormal means unit length and perpendicular, right? So that just means that the inner product of two of these things, e to the pi I pi nx over L, or e to the negative I pi nx, m, sorry, it's not negative, e to the I pi mx over L. So if you take two of these things and you take the inner product, again, a calculus student wouldn't know what this means. But in other words, 1 over 2L negative L to L, they know what this means. E to the I pi nx over L times e to the negative, so the complex conjugate, negative I pi mx over L dx, that this thing here is 1 if n and m are the same, and 0 if n and m are different. That's all that it means to be orthonormal. And this is something that a calculus student can understand. Just compute this integral. Is it 1 or is it 0? Okay, so that's all you had to do for the first problem. Next one, sketch a square wave. Once again, like, not everybody sketched this, and so I'm like, those are free points. Like, please take advantage of those. So square wave, this is, let's see, it's going from 1 from here, and then it's this way, and then you just repeat this. So this goes here, this goes here, and etc. So sketch this, and then find its complex Fourier series. So you got to find C naught and Cn. So C naught, first of all, is the average value. So you can just look at this and say the average value is 1/2. You don't have to actually compute anything. If you can compute it, something is 1 over 2 pi times negative pi to pi of f of x dx. And you be careful here. This is you can't just plug in 1. This is 1 over 2 pi from 0 to pi of 1 dx. And again, this is going to be, so this is 1 over 2 pi times pi, and that's going to be 1/2. You didn't have to compute the interval. You could just, by inspection, say it's 1/2. And then Cn is 1 over 2 pi times negative pi to pi f of x e to the negative I n x dx. So that is really just 1 over 2 pi times 0 to pi times, so the function is f is 1 on that interval, e to the negative I n x dx. So that's 1 over 2 pi e to the negative I n x over negative I n from 0 to pi. So you plug this in, that's, let's see, 1 over 2 pi n and negative I. So I can put the negative I on the bottom, or I can move it on top and make that positive I, because remember, 1 over I is negative I. So I'm going to write that like this, and then I'm just going to plug in, if I plug in pi, remember that also, side, e to the I n pi is negative 1 to the n. Same thing with plus or minus, doesn't matter. So this is negative 1 to the n minus e to the 0 is not 0, is 1, and that should be your final answer. And you don't have to plug it back in. I mean, if you tell me what C naught is and Cn is, that's fine. Okay, problem 3. Consider the following function. So this is a parabola type thing, x cubed, and then sketch the odd extension. So the odd extension is first make it periodic, so make it odd, and then make that periodic. And then the even extension is take that and make it even, and then make that periodic. I mean, it's just sorry, it's not perfect. It's supposed to touch that axis. You get the basic idea. So some of you made like odd functions, but they weren't periodic, and I've done this enough to see that. So some people would like draw this, and then they would continue drawing it. So wrong answers that I've seen and I continue to see are things like, oh, let's make it do something like this. Like this is an even function, but that is not a periodic function, so it's not the even extension. So I think there were like 2 points for that, 1 each. And then the Fourier sine series, for this one, I give you the definite integral. What you have to know is you have to know that Bn is for 2 over pi, from 0 to pi. So times the function, so this is x cubed sine of nx dx. And so that is this, and so the answer is this thing here, evaluated at x equals 0 to x equals pi. Let's think about what that is. So if you plug in, so sine of n pi is 0. So let me see, so 3 something times sine of n pi over n to the 4th. That right there is 0, so that whole thing goes away. Minus, and then you have x n squared pi squared minus 6. Cosine of n pi is negative 1 to the n over n cubed. And then you have, and then you plug in 0, so sine of 0 is 0. And if you plug 0 into here, well, if you plug 0 into here, that's going to go away. So minus 0 minus 0, so the answer is going to be, let's make sure that, so it's going to be, oh, hold on, I put x here, I got to plug in pi there, so this is pi. So the answer is going to be 6, it's basically that. 6 minus n squared pi squared pi times negative 1 to the n over n cubed. So that's what Bn is. And this is a sine series. You do not have to compute an or even a naught. The idea is those things are 0 anyway. If you did compute them, they would be 0. Unless you computed them wrong. If you did this formula with cosines, you are computing an an of a different function, which is not correct. So again, most people did better on this than I normally expect. Those things are subtleties. I always get people trying to compute b naught or an or a naught, and if you do it right, you will get those things are 0, but if you use the wrong formula slightly, like, again, shading this with cosine, you get something that's non-zero, and that's not part of the Fourier sine series. That's part of the Fourier cosine series, not sine series. Okay, problem 4. There's a sawtooth wave, and so extended to be 2 pi periodic. I probably should have done this in the variable t instead of x, but we're just so used to x being variable. Here's the Fourier series. Describe what physical situation. So there's really 2 things I'm looking for. The left-hand side is simple harmonic motion, like a mass spring system. And then the right-hand side is the forcing term. So that means that the external force is this sawtooth wave. So you had to say both things for full credit. I don't care if you say simple harmonic motion or mass spring system. I'm going to assume there's no damping unless you say otherwise. That's what simple means in there. So then find the general solution. What also another thing you guys I think seem to do better on than most classes is majority of people looked at this and said, okay, right away I know that the homogeneous solution is a cosine of 2. I should have done t. A cosine of 2x plus b sine of 2x. I will get people who do that wrong, or who plug in and do it not by inspection. It takes a long time to do it, but you guys seem to be better at this than I'd normally expect. So that's the homogeneous solution, and then for the particular solution, this is x. What some people did is they just used this as a particular solution. That is not the particular solution. So nice try though. What you have to do instead is you have to. The particular solution will be a Fourier series. And normally, you would say, well, it's a naught over 2 plus n equals 1 to infinity, an cosine of nx plus bn. So some periodic function. Now imagine if you did this and you plug this back into here. So you take 2 derivatives. So if you take 2 derivatives and you plug that back in here, and you collect terms, then you're going to set the sines and cosines equal to the right-hand side, which is this. And the right-hand side has no cosines. So you don't actually need cosines in here. In other words, you can just, you can assume that's 0, assume that's 0. So in other words, let's write this yp equals bn sine of nx, and so the second derivative, yp double prime, is negative n squared bn sine of nx. So you plug this back in, and so plug in, and you get the sum of negative n squared bn sine of nx plus 4 times the sum of bn sine of nx, and you have to set that equal to that, which is the sum over 2 over n, negative 1 to the n plus 1 sine of nx. And notice, because there are so we're going to collect terms. Actually, I'll save what I'm going to say for later. So this is 4 minus n squared bn sine of nx. See what I did? I combined these two things into that. And that equals the sum of 2 over n negative 1 to the n plus 1 sine of nx. So we're going to set that equal to that. Let me say it differently. We're going to set that equal to that. In other words, solve for bn. And so what this says is that bn equals 2 over, or 2 times negative 1 to the n plus 1 over, n 4 minus n squared. Did I do that right? I'm making sure I didn't miss something. Yeah, so what that means is that the general solution is homogeneous plus particular, which is a cosine of 2x. Should have used t. B
sine of 2x plus 2 negative 1 to the n plus 1 over n for whatever this function is, sine of nx. So that's your final solution right there. I feel like there was something else. Oh yeah, I know what I was going to say. So imagine, it's worth seeing this. Imagine this left-hand side was like y double prime plus y prime plus 4y. Or so suppose that there's a y prime in here. And when we had plugged this back in, what we would be getting, instead of, so because we have the second, so the function has just signs and the second derivative has just signs, if we had done a first derivative, oops, let me use the, try that again. If we had done yp prime, it would have been nbn cosine of nx. And if we had plugged that, and that had arisen in the left-hand side, there was no way, or should maybe do up here, there's no way that would cancel with just signs. So that's kind of my hint here is, in general, your particular solution is going to have sines and cosines in it, but because there is no y prime term here, we don't actually need to have a cosine. So we don't need to have this term because we won't introduce, if we only have one derivative, we introduce cosine terms by differentiating sine terms, which does not happen if we just have a second derivative. Finally, the last problem. I'm aware that I did not put a Sturm-Liouville or boundary value problem on here. I will absolutely put a boundary value problem on the final. It's just there's only so much I could do in hour 30 minutes. So here's a differential equation. Is this a x equals 0? So the first thing to do is write this as y double prime minus 1 over x y equals 0. This is a singular point because this is not defined at x equals 0, but it's a regular singular point. So I think so there's the y double prime plus p of x, y prime plus q of x, y double prime, sorry, y's no primes equals 0, and if x p of x and x squared q of x are analytic, are defined, which they are in this case, it's regular. I should write neater. Regular singular. So it's a regular singular point. And so to find a solution, assume that this is your y. So let's do two derivatives of this. Y double prime equals n equal, here I'm going to keep the indices because you got to be careful with this. N plus r minus 1, a n x to the n plus r minus 2. Actually, what I'm going to say, x minus r minus 1, and I'm going to put an x right there. So x times that. And so I'm going to do something slightly different. I'm going to minus n equals 0 to infinity of a n x to the n plus r. So what I'm going to do is I'm going to basically plug this back in, and this thing here is x y double prime. This thing here is minus y, and I'm going to set that equal to 0. So I'm kind of plugging it in and all at once. So to combine these things, you have to shift up these indices. So if you do that, you get n equal, so n plus r plus 1, n plus r, and I'm not going to go through the let m equal things. If you do this enough, you just get used to that. Y n plus 1, x n plus r, and I'm going to write that as x. I'm going to put the x to the r out here. Minus x to the r, n equals 0 to infinity, a n x to the n equals 0. And because we're shifting indices, you've done this enough, you replace every n with n plus 1, but this n equals 0 becomes n equals negative 1 to infinity, before you can combine these, you got to pull out that negative 1 term. And also, right away, this x, you can just divide through by x to the r. That is going to go away. So the r equals 1 term happens when, so when r equals 1, we have n times n minus 1. Oh, sorry, not r equals, n equals, when n equals negative 1, we have r times r minus 1 times a naught times x to the negative 1. And now you can combine n equals 0 to infinity. You can write this as combined terms n plus r plus 1 times n plus r times a n plus 1 minus a n x to the n equals 0. So this thing right here gives gives the recurrence. This is part C is this r equals 0 or 1, and the recurrence here is that a set that equal to 0. You get an plus 1 equals 1 over n plus r plus 1 n plus r an. So that's the recurrence that. So that right there, that's parts A, B, and C. And the first value of r, find a1, a2, a3. So let's do r equals 0. If r equals, and also I want to emphasize that this thing, I mean, I'm solving for an plus 1, but in general, this is an plus 1 times, well, I'm going to actually, well, yeah, so n plus r plus 1 times n plus r equals an. So for r equals 0, so when r equals 0, this is going to be a n plus 1 equals 1 over n plus 1 times n times a n, and you know, and so you plug this in, and you say, okay, well, what about n equals 0? Well, n equals 0, you're dividing by 0. That's a problem. Doesn't mean it's not defined. You just have to be. This is where you look at this and say, okay, well, what happens when n equals 0? When n equals 0, what we really have is we have a n plus. So I'm going to move this over here. You have a n plus 1 times 0 plus 1. 1 times 0 equals a naught. So what that means is a naught is 0, and a n plus sorry. Let me. Well, when n equals 0, we have, I call this a n plus a1. So when n equals 0, a1 can be anything. I mean, like, but a naught has to be 0. So what this tells us is that a naught has to be 0, a1 can be anything, and then a2 is in terms of a1 and a naught. So let's see. So a2 that's going to happen when n equals 1. A2 is 1 over 2 times 1 times a1. A3 is 1 over 3 times 2 times a2 equals 1 over, so that's 1 over 12 times a1. And so what you get is you get y, I'm going to call this 0, of x equals 0 plus a1 times 1/2 plus 1/12. Sorry, the n equals 1 term is 1/2. So this is 1/2 x plus, let me make this a little bit clearer, just write neater. So you're going to get a 1/2 x plus 1/12 x. What did I say? No, sorry. A1 is the coefficient of x. Now the coefficient of x squared is a2, which is 1/2 x squared. and now the coefficient of x cubed is 1/12 x cubed, and if you do one more, you don't have to, but it's 144 x to the fourth, and it just goes on forever. So that's when r equals 0. When r equals 1, let's do this one in a different color. So when r equals 1, now you actually get a1 occurs when so r equals 1, a1 is going to be 1 over, I should actually probably, let me do this. When r equals 1, it's worth writing this down again. You have a n plus 1 equals 1 over n plus 2 n plus 1 a n. So now you have a1 is a naught over 2 times 1 is 1/2 a naught. A2 is going to be 1 over 3 times 2. A1, which is going to be 1/12 a naught, and then it's the same recurrence, it's just shifted, etc. So A3 is going to be 1 over 4 times 3 times A2. So that's 1/12, so it's going to be 1/44 a naught. So y1 of x is going to be a naught times 1 plus 1/2 x plus, again, same recurrence, just we're shifted up, x squared plus 1/144 x cubed. And a basis for the solution space is y0 of x and y1 of x. You can write it like that, or you can write it as this with this, and the general solution is literally this plus this. So the general solution of y of x, you can write it as like a naught times this plus a1 times this, or you can write it as like the a naught times 1 plus 1/2 x, however you want to write this. I was kind of lenient on, on your notation here, plus a1 times x plus 1/2 x squared plus 1/12 x cubed, etc. Okay, so that's the end of that. If you have any questions, please let me know, and good luck on your final.